Hello everyone, welcome back to Causality with Boris, broadcast from SobolevSpaces. In this video, I introduce conditional independence. I'm going to talk about common cause and spurious association between independent variables. Then I unravel the consequences of stratification on common effect. Make sure you watch to the last chapter. We'll talk about the Berkson paradox. There will be extra material for this video. Click the link in the description, it will be sent to your inbox. Let's take a look at dependencies among three variables. Before we move on, it's worth spending a moment on our running example. In this study, mortality is compared by timing of hip fracture surgery. Early and late surgery groups may differ by the proportion of medically stable patients. These patients are ready for the operation when they arrive to hospital. They may also have a better chance dealing with surgical intervention. This difference is important. It can bring us about the association between timing and mortality, even if they are independent. Most causal thinking revolves around this fundamental problem. The outcome probability might be different between treatment groups because of other factors, not due to the difference in treatment. How do we rule out non-causal association? When we look at two variables, we check their marginal probabilities. When a third variable is involved, we work with conditional independence. Mosaic plots depict association between two variables. Now it's time to try it for three. As always, X is for treatment and Y is for outcome. Now let's add Z. It denotes variables that influence both treatment and outcome. We divide the unit square into 4 vertical bars, one for each treatment group across the strata that Z define. For instance, the bar on the left corresponds to X and Z being 1. The vertical bars then divided into rectangles. Their areas are joint probabilities for all three variables. The orange rectangle on the right is the joint probability that X is 0, Y is 1, and Z is 0. Rectangle heights are conditional probabilities that Y is 1 given values of X and Z. We use their heights to check for association. Variation in heights shows association, right? In this plot, their heights change with values of Z only. We say X and Y are conditionally independent given Z. Conditional independence is a powerful tool for exploring associations. Our first case is a common cause. This graph shows dependencies among three variables. Arrows are the direction of dependency. We see that both X and Y are dependent on Z. In other words, Z is their common cause. We also notice no dependency between X and Y. So, what happens when we explore their association but ignore their common cause? Let's make it more interesting. Here's another real-life example. Medication reviews. 1 in 9 people who come into emergency department need treatment for adverse reaction to prescribed medications. Yet it's diagnosed only half the time. Medication reviews by a hospital pharmacist are set to spot adverse drug events. Let's see what conclusion we can draw about the effect of this measure when we ignore hospital type. Here's the thing. Both medication review and adverse drug event may depend on hospital type. Big hospitals may have funds to hire pharmacists, so reviews are more likely in teaching than community hospitals. And more medications are routinely prescribed in the catchment areas of teaching hospitals. Same mosaic plot. X denotes the presence of medication review. Y is an indicator of adverse drug reaction, and Z is hospital type, teaching or community. Our common cause graph shows no dependency between X and Y. So we expect the joint probability for X and Y to be equal to the product of their marginal probability. Let's find out. We can read probabilities of the orange areas. Let's see how to find the joint probability that Y and X are equal to 1. It's 1/4 the area's width multiplied by 1/3 its height plus 1/4 times half. That's a 20 out of 96 probability. Now let's find the marginal probability that y equals 1. We just sum up all joint probabilities where y is 1. The sum is equal to 20 over 96, that's a joint probability we just calculated, plus the sum of 1/8 times half and 3/8 times 1/3. This makes a 19 out of 48 probability. Then we look at the marginal probability that x equals 1. Summing up all joint probabilities where x is 1 makes 1 in 2. And now let's compare the joint probability for x and y with the product of their marginal probabilities. The joint probability is 20 in 96. The product is 19 48 times half or 19 in 96. They are not equal. It means medication review appears to be associated with finding more adverse events, even if there is no connection. Interesting, we assumed no dependency between x and y. The mosaic plot shows no dependency between them for each z, and yet ignoring z makes x and y associated. Ignoring z means this: the observed probabilities are naturally averaged over the distribution of z in the population. Let's check it. First, we calculate probability of adverse event given the medication review is in place. This is shown as x equals 1. It's 1/2 times 1/4 plus 1/3 times 1/4 divided by 1/4 plus 1/4. That's a 10 out of 24 probability. Then we calculate probability of adverse event given that there is no medication review. X is 0. It's 1/2 times 1/8 plus 1/3 times 3/8. We then divide it all by the sum of 1/8 and 3/8. The result, 9 out of 24. So when we ignore hospital type, probability of adverse event is larger with medication review than without it. And we conclude that the review finds more adverse drug events, all because a common cause is ignored. Our second case is common effect. Again, this graph shows dependencies among 3 variables, but this time z is dependent on both x and y. That's the reason z is called common effect of x and y. Just before, there is no dependency between x and y. Well, this holds if we stratify on common effect. Stratification means exploring association between 2 variables at different values of a 3rd variable. Here is another example. It helps us understand the counterintuitive result of stratifying on common effect. It's known as Berkson paradox. In 1946, Berkson looks at the connection between 2 diseases. At that time, we thought cholecystitis, another name for gallbladder disease, was a provocative agent for diabetes. Sometimes gallbladder was removed to treat diabetes. He receives reports that hospitalized patients without diabetes are more likely to have cholecystitis. He looks at the occurrence of cholecystitis and diabetes and finds association between them in hospitalized patients. Berkson points that hospital admission may happen because of either conditions. He then quips, patients with gallbladder must have had some non-diabetes reason to be in hospital in the first place. So let me walk you through his calculations. Some new notations. Let Z be an indicator of being in hospital. 1 is for hospitalized. Let X denote the presence of cholecystitis. Tilde X, its absence. Similarly, Y is the presence of diabetes and tilde Y, its absence. Next, we need some assumptions. First, the admission rate is different for both conditions, or either condition, or for having neither condition. Then, let's pick the joint distribution for X and Y that guarantees their independence. How about this? Any combination of diabetes and cholecystitis occurs 1/4 of the time. And now, let's show that X and Y are associated when Z is 1. Conditional probability of X when Y and Z equal 1 is 12 over 25 divided by the sum of 12 and 13 divided by 25, which is 12 out of 25, nearly 1/2. And the probability of x when z and tilde y equal 1, 3/4. Here it is. One probability is larger than the other. Negative association. Risk of cholecystitis is higher in patients without diabetes, when they are in hospital, of course. We just saw how two marginally independent variables appear dependent. All it takes is to explore their association when the variable that depends on both is held constant. This video is about dependencies among three variables. You learned that ignoring common cause brings about the spurious association. Treatment and outcome seem to be related, even if they are independent. But you also learned something else. Independent variables will be associated if we hold constant the variable they both affect. Here is my main message. When a third variable is considered, we are working with conditional independence. Conditional independence is a powerful tool. We use it to look into the relationship between treatment and outcome when other factors come into play. That's it for today's lesson. Stay tuned for another episode of Causality with Boris. Keep on watching.